Hello, everybody. Welcome to Mankind in Training, the Wolfram Alpha Quantum Computing Live Study Group. I'm here today to share with you again. If you are not here, it's all right. You can catch the video. It'll be posted online. It'll be fine. So, today, what we're going to do is we're really going to get into unpacking what's going on in this framework. This quantum computing framework of Wolfram Alpha. It's a beautiful thing. And aside from the quantum packlet, Wolfram Alpha, Wolfram Mathematica is just amazing. It's absolutely incredible. I'm gonna promote it, promote it, promote it. It's so awesome. I really have been glued to my computer. It makes computing things fun, and I love it to death. I have some examples here that show a little bit of what's going on, a half decent way to look at what's going on. But I want to get into unpacking. So here's the thing. Everything in the universe, as we know it, can be computationally represented in this framework, and that is the purpose of it. So with that, like I was saying in the last session, you can create states that you couldn't possibly see in nature. And then, I mean, we could do this before, but it wasn't easy. It wasn't an easy thing to make a model with these states interacting with states that we know what it does to a matrix representation. But when you do a rotational X to a single X uh, basis state, like we know what that looks like. So if we do that same exact operation on one of these faux states, we have an idea of how to disengage like which part was of this operation is the known and which is the unknown, and we can sort of differentiate the two states from there, and we can sort of make out a way in which that fake state we derive some real parts of state that we didn't even know existed. The implications of that are incredible, and the framework is friendly to the fact that you can make these crazy states. Oh, I 350. I don't like that. I don't like 350. I was hoping for one. I may not need to do this every time. I've been doing it every time because several times in a row it didn't work if you don't do this. Wait for your Packlet object to appear because it is still running. So we have a basis state made up of qubits. These qubits, this is what a state is. These qubits have a position, a spin, if you will, that points towards a direction on the block sphere. We have a block sphere representation for a state, and the state can be a matrix representation too. It can be, you know, there's a lot of different ways in which that you can represent a quantum state, but there's a lot of different ways that you can like derive a pure quantum state out of, nonsense. So we're trying to synthesize like an arbitrary complex numbers phase angle, like for the base state anyway. And like internally in this packlet, uh the associations are being derived by like a compilation of tensor products and like associations of those like constituent operators. So think about like an S matrix representation of uh, a state, a basis state, and it's in a branchial space, or it's in a rulal space, or you can think of projecting it onto like into Hilbert space. But here's the we're usually always representing projected metrics that have been like the Riemannian or technique where you project the infinite line onto a circle in order to make things a lot easier to compute. When you don't have an infinite line, you have a circle that you can re return back to yourself at whatever pi r. You can get back to that position. So like these tensor state vectors that are being created, there's like transformations into matrix representations that are explicitly given by these named operators that this packet has. So like a C naught has two inputs, say. So that certainly is going to be acting on a circuit that has two qubits at the very least. So let's go into this and unpack some things here. So if I have a quantum uh sorry, if I have a quantum state, I'm going to choose no, let's do operators so you can really see. I don't know. That doesn't make any sense. So there is a state, phi minus. It's a matrix in matrix form. So here's a quantum operator. XX. And I want the matrix / matrix form. So that's what's going on here. This is a XX operator. Now, if I take this XX operator and I instead do a rotational X operator, I get this. Now, a good way to explore what this is looking like. So here's the XX operator. Any one that you see is the color in the array plot. And the matrix plot is going to look just like that, except this has color to it. It's going to have a color of uh I'm not sure if it does it by weight or like the heat maps do in the normal objects. Uh it's for the sake of the learning. Even the picture looks like this. It is showing what's hot and what's not. The ones are across the way. Now, the matrix plot of this rotational X operator takes this and flips it on its head. So wonder why I did that. Um, I wonder why that is happening. There we go. That's what we want. Okay, so that's just the XX operator. And the rotational X operator looks suspiciously like the XX operator there. So I wonder why I can't do the matrix plot of this now. Yeah, I wonder why it won't let me do that now. Huh. Anyway, I was trying to show you what a rotation looks like but it doesn't seem to want to do that for me. So quantum state. I should just go through the documentation because they have everything you would want to know. Um, so here, yeah, I'll just stop what I'm doing for a second. You can see I made it a little bigger and I did a rotational X. So originally the base of ones is just a single line down that way. When I increase dimension, I get a mirrored effect of that, which probably has implications in and of itself. So okay, so when I do two rotations of X, it lost this whole middle line here. It changed significantly how that is displayed. So you did do it. Oh, it's because I need a second X. Yeah, there we go. So this is an X state or an X operator, a Z operator, and an X operator. I think they're all Pauli distincted. And this is a rotation X, and then another rotation of X. And as you can see, it was on a different axis in this branchial space, and now it is different indeed, going the opposite way, and it's been split. So it has the same amount of bits, as you can see, but one's been shifted out. They both were right down the middle, so they're both offset by just one row in the matrix. That's really all this is a hot knot matrix representation. So when I look at the matrix of this, exactly where all these pins are, the white blips, there will be a 1 or some value that isn't 0 in the sparse array or the matrix. So that is a really good way to think about what's going on when you do things. Here's a matrix form, and that's, as you can see, not down the center, but right off to the side of it. Oh, that's kind of odd. That looks a little weird. That's weird. That's more like it. Well, it normally is anyway. When they adjusted it out, probably because of the amount of qubits, so this is a normalized matrix. Maybe if I just let it flow crazy, it'll... Oh, that's cool. I didn't think it was going to do that. Okay, so I'm going to go out to the documentation where the good stuff is at. That's just I thought a good way to maybe teach you guys how to think about what you're even doing. The best way, though, to think about what you're doing. So let's break this down. Let's get down. All right. So if I have this circuit in particular, so I have 3 states. I have 3 basis states. And it's only a basis state over here before it's gone into this circuit, or before it's been operated on at all. After identity keeps getting operated along the circuit. So as you go along, you have 3 qubits. So what's the word I'm looking for? I'm drawing a blank on the dumbest word ever. Conveniently, no, not conveniently. The convention is that hopefully these qubits that you have on either side of the circuit are entangled. I still can't think of the word I was trying to think of, but anyway, you want them to be entangled. So the qubit starts out, they all 3 go at the same time. This qubit doesn't get operated on until the 3rd. You shouldn't think of it as a time step, but just maybe a state cycle or something, because we're not entirely ER equals EPR. If it's entangled, you got time may not be a thing so much that we could measure it at all even. So you have a Hadamard gate, Hadamard operator on these 2 qubits, and then an X operator on these 2 qubits. And then you have a controlled knot here, and then you have a not, and then you have another X, and then you have another X, and then you have another Hadamard, and you have another Hadamard, and then out come three new states. All three of them have been operated on in some way, and you now, when you take a measurement and collapse the circuit on any of these, there isn't a measurement in this circuit, but when you do measure, because you do have to eventually measure these qubits, or you're not. I mean, what's the point? What is the purpose of what you've done? But um, a good way to really get understanding what's happening is to go to this Packlet repository and go to the getting started and go right down the row. State, operator, measurement operator, measurement, tensor product, partial trace, go all the way down the row. Look at all of these examples, and when you get to the bottom, there's more examples. That's not the end right here. There's 100 more examples that show you how to designate specific phases, names, basis, where to put your measurements, why you're even doing it. There's explanations in between. You should read this front to back if you want to be good. If you want to be good at any, well, and this is true of any programming language at all, really. If you want to be good at it, you have to practice, you have to read, you have to learn. Here, you should start from the beginning at states basis. Quantum basis is another thing. The whole list is over here. So, maybe that's a good thing to click on. Quite simply, you can just call quantum basis and just 2, and it'll make you a computational quantum basis of 2 dimensions. Same thing. It just by default will give you a computational basis. You can designate in the normal uh, Schrodinger and Dirac notations, you can uh, just write it out like that, and it will take your state by, they call it element association here, the Dirac notations for what's going on in the state. So I'm gonna go over to here. Create a quantum circuit composed only of single qubit gates. So he's doing an X operator and a Y operator, which are just single qubit gates. And he's coupling 2 here, which is weird. That usually when you do that, it does a measurement up. Oh, it's inside of that quantum operator. Yeah, okay, never mind. Yep. Yep. That's just designating that X is on the first circuit line and Y is the name of the operator on the second qubit line. Draw the associated circuit diagram. You just call it diagram. Quantum. It's a C naught and a Hadamard on 2. So if you close it and it's in a square, if you close it in the square with the angled brackets, it will designate that it's just on 2. And if you have it open, it will assume that you want it on both of them. And that's like just 2. You would want, in order to maybe reap some of these quantum benefits, you're going to want Fourier transforms. Those have been really the only thing historically that have been successful thus far in actually shortening up like operational steps and doing something where we can do something with a quantum computer. Like really, we can really do something with a quantum computer, like Shor's factoring algorithm, for instance. Like we can actually do that, and it is faster than any. We have no computer that can do what Shor's algorithm did. So here's a Toffoli gate. This is a fancy gate that is actually used in Shor's algorithm or Shor's circuit. The Bell diagram. It's got a Hadamard and a controlled knot, and then a Toffoli transpose operator, like a Toffoli single qubit operator, and then another controlled knot out to 1. There's like a diffuse pattern to it. For the quantum Fourier circuit, we have a quantum circuit operator, Fourier, and you can distinguish it. Fourier is they've made it comparable. You just add whatever dimension you feel, and with the number of qubit anyway. For example, like the Fourier circuit of 2 qubits looks like so. It's got a Hadamard operator. It doesn't get operated on until controlled pi to the half operator. There's a Hadamard operator. Swap, dead swap on 2. The inverse Fourier is exactly as it sounds. There's a swap, a Hadamard here, pi to the half, a knot, or I don't know if that's a knot. It's a something. It's a something here, and then this is not here. It's there, and then there isn't anything. So this is a 5 qubit. So thinking about this, this is neat. So 1 qubit, we have 4 states. 2 qubits, we have 8 states. 3 qubits, we already have 32 states, I think it is, and then 64. It grows exponentially larger. For the quantum phase estimation, we have a quantum circuit operator, phase estimation U and N, which takes 2 input arguments, the unitary operator and an integer N. An integer specifies the number of qubits and the controlled negative U to the J operators in the circuit. So with J equals 0 through all the way up to N minus 1. The accuracy of phase estimation and the success probability depends on N. So we got quantum circuit operator, the named operator phase estimation, quantum operator again, calling phase operator, and then designating that the phase be 2 pi over 5, and then it does a factoring, a step down for like a polynomial step down. 3. There's Hadamard's at the beginning here and an X gate at the bottom, and it only measures the Hadamard circuits, it looks like. I don't see a measurement on 4. So that's one thing I need to read up on and understand a little bit more. When you have a circuit but you don't measure it, what is the reason for not measuring the circuit? What is the reason for having the circuit then if you don't measure it? I can understand maybe that's part of the reason that they have success in some of these things is that they do a swap. They do a swap on a qubit and learn a phase that they shouldn't have been able to. Because technically, I don't. So with the entanglement, they've proven that there's wormholes. They can create wormholes because they did. Well, there was a one qubit in one circuit line, and another in another circuit line, and there was like an ion trap, and they traded them. Given a graph, the corresponding circuit which generates quantum graph cluster states is a series of controlled Z operators on edges of a graph. And this is a hypergraph, zero-dimensional hypergraph that can be manipulated in every which way. It can be turned into a incidence matrix and a Kirchhoff matrix, and it can be turned into a this matrix and a that matrix and a this. There's so many different functions in Wolfram. It's amazing. Here they're taking this random graph and turning it into a quantum circuit operator with these parameters. Open junction, no directional purpose in that one. For the Bernstein-Vaziriani algorithm, one needs to specify a string bit as follows. So for the oracle, we have quantum circuit operator and the Bernstein-Vaziriani oracle, and S. For the whole circuit, E quantum circuit operator, Bernstein-Vaziriani S. For example, the Bernstein-Vaziriani oracle for the secret bit of 101. And you have the oracle, and it's got this complete controlled knot, and then a smaller controlled knot, and then the oracle operator, which pulls 101. The Bernstein circuit for the secret bit of 101. Quantum circuit operator, Bernstein-Vaziriani 101. Diagram. It's got a bunch of Hadamards and a Z operator at the end. The BV oracle which we just discussed up here. 3 more Hadamard operators, circuit operators, and then they measure them off one at a time, and that's kind of what I was talking about in the last session. So if you pull a straight measure, you say you have more qubits than this, and you had a big great state full of all the information that you need. If you can keep your state entangled, you can lower the steps of this problem by so much. If you can just keep your answer, well, we've been pulling. We did a measurement on all 6, all at the same time at the end of the circuit, and then they met up with somebody who understood a little bit better what was going on, and he said to them, "Well, what is the purpose of measuring them all at the same time?" They said, "Well, don't you have to measure it to get the? Don't you have to measure it for it to be worth even going through the circuit in the first place?" And the physicist says, "Well, of course. But if you measure them all at the same time, you lose the purpose of having a quantum circuit in the first place." And they say, "Well, what do you mean?" And he says, "Well, what do you mean? What do I mean?" Oh, you've basically just made a long, fancy, complicated normal circuit if you just measure them all at the same time, because you're collapsing the measurement on all of them on the entanglement of all of them all at once. If you fetter it off one by one, you can actually decompose the states backwards through the circuit and find out, what a lot of these superpositional states were. You get a probability density measurement of what they were. So there's a collection of named circuits for the Grover search algorithm and its oracles. The Boolean and phase oracles, or amplification. The class of Grover-related named circuits are quantum circuit operator named Boo with a Boolean function, a Boolean oracle for a given Boolean function. Actually, you know what? I had a different. Let's go to multi-way Turing machines for a minute, because I have to cut tonight's a little bit short. So this is, I think, let's break this down to the quantum state and then a quantum operator. So a quantum state is at any given moment, say there's this series of associative positional nodes like this in a graph. We have this. In all of these, you should think of as so each of these makes up one of the amplitudes or the keys of the associations in this state, because there's multiple. At the end of when you get a measurement, you have a whole thing, but it could have been any of these things. And that's what this multi-way Turing machine is kind of representing here anyway, is that this is the sum of all of its parts. And it happens in this way. So if you don't give it implicit instructions like this, you just say that these are the states and give them away, but let them evolve in such a way that they gravitate towards each other naturally. How just arrange them how they would and throw them where they lie, and you can make all of these into quantum states. So you should think of this. I was back to what I was talking about. So think of this particular graph. Maybe this Turing machine isn't maybe supposed to. Well, it is. Yes. So this is states. So associative states graph. So like we have all these states, and at any given time, you should think of a quantum operator as being a change in state. So we delete this altogether and add that part to this, and it gets moved over to here, and it changes the whole graph. Say that happened. That was the evolution you measured, and that's what the state was. Or we have a motion operator on the quantum state that breaks all of these composite singular parts into a full bar and shortens the tree up and makes it a little more even on either side. Makes it more like a decision tree that didn't ever land on a small hot. It was it mostly landed in the above 10% range in probability densities for these states. These either on or off states. A Boolean Oracle multi-way Turing machine. Anyway, I thank you guys for watching. Thank you for studying. Thank you for learning. Thank you for being along for the ride. And quantum computing is going to take off. It's a lot of people are really skeptical about what are you gonna do? What are you gonna even do with these machines? What do, it's hard enough deciphering anything about what we're trying to do here, let alone we're gonna change the world. No, I believe we are going to change the world, and there's been an explosion. There's been just an explosion in interest. There's lots and lots of interest in quantum computing. Actually, it's a hot button topic. There's probably going to be lots and lots of. By the time I graduate, there's probably going to be a master's degree program in quantum computing that I won't be able to get into because I didn't get like a bachelor's in quantum mechanics or anything. But I see, I think you can get just certified anymore and be considered worthy of uh, thinking about fundamental physics. But I, I, I don't know. Really breaking down everything that's going on. That's a good one. I like that. Tree with weights. Anyway, thank you guys for watching, and like I said, thank you for being along for the ride. Tomorrow it'll be a longer session. I have a lot of good examples, because I've been just actively, vividly researching exactly what I was saying. There's so many faux states that you can create, and maybe there's, you know, a state that you can create that you think wouldn't exist in nature, but because of things that you did to that basis state or to that operator that you created, you made it into a real thing. You found a real part of it enough to the point where you could derive the real thing. And the implications of what you could really do with a quantum computer if we were to get, say, just an inordinately large amount of qubits entangled. I really want to work on the hardware side of this problem because I I see the beauty of this quantum framework, and I see the beauty of using entanglement to boost computational ability, but and there's supposedly there have been successes, but I feel like we have a long way to go. Uh, like Google has a roadmap where or IBM, both of them are releasing, these quantum machines with a few more qubits at a time. I There's got to be some other way that we could go about doing an entangling system to use for computation, where you could where the amount of qubits you could entangle is trivial to the amount of space in the system. Like I think we can get to that level if we. I have so many like experiments that I want to try personally. I need equipment though. Need a lot more equipment than I have. I have a prototype that I'm going to build, but I think that's only going to just demonstrate what I'm talking about. I need more I need far more precision measuring equipment if I want to actually see if I'm on the right track with that. But anyway, I've been rambling. Thank you, you guys. I have class. I have to go. Thank you for watching. Thank you for subscribing. I will be back tomorrow. Um, what's the time? I will be back tomorrow at say 7 or 8 o'clock in the evening if anybody wants to join me. I really, this is open live. I've opened it. I've sent emails out. Anybody wants to come is welcome. I love physics. I love fundamental physics. I love theoretical physics. I love the fact that you can do every anything physics related that you could think of. They have a documentation page that shows you how to do anything that you want. And Wolfram's so very easy to use. You could begin uh oh man, a beginner could become an expert mathematician. Uh Say in the year that they sign up for a year access to Wolfram. If you actually practice with it every day and like just by seeing the answers of things all the time, I it's incredible. It's that I recommend Wolfram wholeheartedly. This is the greatest product I've ever purchased in my life. It's the most useful tool I've ever purchased in my life. Thank you, Stephen Wolfram, and thank you, Jonathan Gerard, I think his name is, for the packet, and Juan Maldacena, I think somebody was also involved. And uh, thank you, Mads, for the study group of your own. That's actually Wolfram Wolfram is in the Wolfram U repository of classes and things. There's a class with Mads Basrani leading the it's like 5 classes. Thank you all you guys for this quantum packlet. I love it, and I plan on using it probably daily for the whole year until I buy a new year. Thank you guys very much. Have a nice day. See you tomorrow.